Hi, we are live. Hi. So today we'll be going over Keras and transfer learning. This is just before the behavior cloning project. I will also be talking about what you can expect from the behavior cloning project in brief discussion, and also go have a look at ChaufferNet, which is the you can say a neural network framework for behavior cloning of imitating the expert system. Essentially, it is able to drive a real live car based on existing data, and I think it'll be easier once I get to there, explain what's going on. So yeah, quick mention of Keras. Keras is an open source neural network library. It's written on top of TensorFlow and has a lot of best practice convention engineering that comes from a lot of people using TensorFlow for a long time. So it makes implementing neural networks much easier in Keras. There's links to Keras, the official site. This is an example. Below here is the same example for MNIST that we did before in TensorFlow, except this one is done using Keras. And what you will see is that there are a lot less lines. And it's really top down like this. You can see that you can define a model by having a model equal to sequential, which is this the sequential model is a convolution of neural network top down. It's not recurrent, which actually there are some recurrent neural networks inside of ChaufferNet, which is I don't believe it's been has been covered in the any of the lessons yet. I'm not sure if actually it will be covered in self-driving car, but so you can always explore it. There are many examples. Yeah, so let's see. Okay, I don't believe I have gotten this correct because there's some issues down here, but generally the idea is the same. You do a model fit. Um, the callback's not working. We just ignore that for now, and then you get the scores here, and yeah. So when your model is being fit, right? Your model is well, firstly I guess compiled and then gets fit. Just that's just how the pattern goes through. You can see here's other layers: convolution 2D, max pooling layer, convolution 2D, max pooling flatten. They're followed by a dense and a dropout, and then another dense. With activation of softmax, then you get the one hot encoding, and then you can get the predictions of here. Optimizer is actually this is one difference. We call it the TensorFlow optimizer was SGD, so that's the gradient descent optimizer. This one's using Atom. Um, Here's something I've from personal experience. Usually, Atom is a good start. You can just pop in Atom like this, and it will it will do its job. But you can generally come up with a better optimizer by experimenting and hyperparameterizing your optimization to get better than Atom. But yeah, that's just what I've something I learned. There's a lot of there's a lot of good things from Keras. I tried to make this model overfit in 25 iterations, didn't overfit. I guess MNES is just too simple of an example for a deep net with several layers to overfit. But it was worth a try. What I wanted to mention was that um, for larger problems, if you train for a very long time, your model likely will overfit. What you can do here is that you can there are mechanisms inside Keras to for early stopping. So if you seen, for example, that the validation accuracy didn't decrease for like 5-10 epochs, you can tell it to stop because it's not really doing any better. It won't get better. It will only get worse. I mean, that will save you some computation time or resources that you can be doing something else with. And there's another thing that you can do is that you have it always save the best model. So over here, right? This is for example, going from this example here, this is the best at this point. Next one is better than this one. This one's better. This one's better. This one's not better. It's not going to save that. They keep going. It will find another one that's better accuracy. Find the next one. This will save that. And for all these, it's not going to save them because they're not better than 0. You know, it's not better than this accuracy. I figure that's something handy, just in case, even if you don't have early stop mechanism, it's still, you won't be, you don't have to keep going back and getting when your model will be very good and always after like 20 epochs stop at 7, because you're going to be changing your model and you don't like that's a lot of time going back and counting down when your model converges to the best validation accuracy, right? Yeah, so you can do all these things on top of regular JSON and dropout and other stuff. Okay, so transfer learning. Summary of why you might want to do transfer learning. Okay, the reason is because creating your own neural network from scratch, taking the time to train it, and uh, changing all the hyperparameters and all that stuff. It takes a lot of effort, and if you can reuse existing efforts to accelerate your work, then you should. So that it makes sense, right? So that's a way to use transfer learning. So intuitively, I mean, I didn't draw a picture here. I remember at one point there was a diagram in the course material about transfer learning. Um, so if you think about this, right, the convolutional layers, essentially it works to capture and summarizes the feature of the input representations. You can see that the representation go from lines and edges, and it keeps going up to more becomes concepts and stuff like that, right? So if you think about this, if the data set you're working with is similar to the neural network that was trained, and that if that neural network had a lot more data than yours, then it makes sense that you can reuse it by just slicing off the last layer because it already is trained on a similar representation as yours. So maybe you only have 3 labels, and they are instead of let's say 0, 5, and 7, you have them at 0 to 1 and 2, right? And all the other ones you're just throwing them out. Essentially, you're just trying to have you can train this you can slice off the last fully connected layer and flopping your, retrain that layer to say that these features are classified as your new labels, and that will take a lot less time than if you train the full neural network. Okay, yep. Mhm. And yeah, that's the other thing you mentioned. So these are advantages of that, because the large network already seen some variations of the data that you might not be able to have from within your own. And then if you just train on your own data, it's going to will likely overfit. But with the existing network having so much data, it likely will generalize better. So there are some exceptions. If your data, let's see, if your data set is small and very different from original, might make sense from go from scratch. If you're trying to classify Autobots, and the neural network that was already pre-trained is with cats and dogs, then it's not going to work very well. You might be able to use only the first couple of layers, because feature extracting of lines edges are generally going to be same and still pretty useful. Other than that, any higher level representation will not be able to be taken advantage by your new model. Okay, for large data set that is very different from the original, okay, makes sense from scratch, but also still could benefit from initializing with pre-trained weights. It could converge faster because it's trained on something rather than nothing. Um, so for the behavior cloning project, you are given a relatively small data set that is trained on images and labels, from a pre-trained current CNN that you could be you could work with. However, the CNN, it is not very similar to what you'll be training on. You'll be training on images of a simulation with a simulated vehicle on a simulated track, and um, a lot of the CNNs that you'll be using, it doesn't quite deal with similar images. So that's something to think about. Um, I'm going to go through the ChaufferNet, which I think I already have on here. Okay. So the thing is, this ChaufferNet, it is very similar to, it is, well, I wouldn't say very similar, but it is similar to concept to what you will be doing for the behavior cloning project. It is using RNN, which she might not have had experience, but we just go over the general concept of this. Okay. So the general idea is that by well throughout the research for ChaufferNet, the people have noticed, the researchers have noticed that even with 30 million, real world expert driving examples, um, it wasn't sufficient. What was noticed that there are times where you know when there are parked cars, that will still it could graze the car. A lot of times it gets stuck. What they have done to counteract this issue was to add perturbation. You will see like below what it is. It takes the original driving path of driving, and it kind of does a nudges the vehicle to the side and forces the vehicle to recover from this. Quite a few techniques being incorporated on top of that. The, see that. So there's a section on related works. Something to note here is that there are lot of these that is accessible to you. The color simulator, which is on GitHub somewhere. I was able to install the one for Windows. It is not easy to install. It will take some. It will take some work to do for you to install it. Yeah. All right. Let's go into the model. Okay. So the model, it trains on images like this, right? You can see these are different images here. So there's the roadmap, traffic light speed, limit, current agent, dynamic boxes, past agent pose, future agent pose. So this is essentially, let's see. So this is 3-color channel rendering map, stop sign, crosswalk curves, etc. It doesn't. There isn't a very in-depth detail of what these are, but you can imagine this is a curve, but this is a crosswalk, and this might be a lane divider. These are lanes, stuff like that. For this here, for traffic lights, so the dark whites are the stop signs. A slightly darker. Well, they say they call them gray, so slightly darker gray, not as dark as not as light as the lightest gray is the orange lights, and the light gray as green. It's kind of confusing, but that's essentially, I believe this is green. This is green here. Going here, there's red. It seems like this is to do with the trajectory rather than the actual light itself. Okay, and the speed limit. So you can see all these are the same speed limit, but there are times when certain lanes will have different speed limits. So if you're on a highway, um, essentially this is depending on the intensity of these lines here, representing different levels of speed limit. There are times when if you're on a highway and you're on the most right, this is be for the truck lane, and it will have a lower speed limit like 60 miles than these here, which will be 70. And that's a route that the agent has taken. The current agent and the dynamic boxes, these are the other agents, other vehicles, could be bike, pedestrian, stuff like that. Past agent poses. Okay, so this is where the agent was previously, and that's the predicted future pose. So one thing for this is that they are using 80 by 80 images, and the agent is always starting at the same point at time step 0. So the orientation of the agent is theta plus some plus or minus some delta here, so it denotes heading orientation, right? Um, 0. Okay. Choose resolution. Okay, yeah, that's just going over that. So here you can see the ChaufferNet architecture. So this is the main. There's two parts of this. This is the so this is the more the main ChaufferNet. This part is using the agent RNN to do the prediction of what the heading speed, waypoint, and agent box heat map. One thing to note is that the um, the network is trained in a closed loop. So if we think about it, right? I think it's easy to well. Thing is, RNN wasn't introduced to a lot of you guys from self-driving car, but if you think about this, right? A closed loop. So recurrent neural network, it remembers the previous time step. It remembers what happened before. So an open loop would be uh, think like this. So a lot of times recurrent neural networks, one thing that recurrent neural network is utilizing is like you can predict stock the movement of the stock market and say a open loop training would be where you take the first 5 days, you predict some number of the next couple of days, and you compare that against what happens in the next couple of days. But you don't use that to predict the days beyond that. You go back to the ground truth. You go back to what data was available, and you use that to predict the n days afterwards. The thing, this is actually what I've used, for example, my own, and I found out that it turned out to be very awkward. The the accuracy or loss was very low, and the final result was not very desirable. It just keeps going in the same type of loop because upon what you call feeding back to itself, it sees the same pattern and it kept going. Um, so yeah, this ChaufferNet is trained on a closed loop um, simulation, which is the better way of doing it. Okay. So there's two parts. This part is the agent, the training of the agent, and there's another separate part. So there is a road mask net. This will be a convolution neural network that gets the road mask, and there is another perceptron RNN. So this gives the heat. Um, so this is predicting where the other agents are. So things like this. Okay. Um, so these are trained in parallel. So A and B are trained in parallel. You can see this a lot of the world real world or the research neural nets they try to do a lot of things at once. So what you can imagine is like this is like a output like an array, and this is the first label is heading, second speed, waypoint, and things like that. And you generally see a lot more than one model like this, which I believe we've seen in previous papers as well. Okay, let's set the object sample over this. Oh yeah, so there's something to mention here that it was shown that using just the raw sensor data it's not was not sufficient. There was a lot of issue doing that. And you can see this is like high level data information. So these are like there will be sensors that would scan these surroundings, and um, they will be summarized into information like this, which something like ChaufferNet could use and do very good driving with. So this is something different from what you'll be doing in the behavior cloning, because you are using the raw pixels for most part. Of course, you don't have to, but it's not a requirement. But that was uh, that was the default rubric, I guess. Okay. That's okay. Filtration pose. Okay, so this is just going through ChaufferNet. So memory is updated in multiple iterations. This is the schema of the ChaufferNet. So let's see if you can see. Let's follow this through the render image plus the past agent locations is being fed into the agent R, and it's going to predict the agent location, and it will add that in a feedback loop of a closed loop. K, that is a time step here. A feature. So okay. So there's also, of course, the features are extracted from FeatureNet to feature. It's going to get the features, and it's going to pass them to the agent R, and okay, so it will. Okay, it takes the last agent box. So agent box is also, so aside from location 8, the agent bounding box is also part of prediction. Right? The output, so yeah, outputs both of these, and then it will feed um, feedback it into itself like this in a closed loop prediction. Okay, so parts for that. Yeah, okay, so that just, and this is so one thing, this is one way you could do end-to-end driving pipeline. Um, so one thing is that it doesn't, one thing mentioned here, it doesn't make sense to use quite makes sense to use behavior cloning to output low-level steering and acceleration control. But of course, the way it sets up, is set up, you can use this to use the control optimization rather than neural network to do the low-level steering and acceleration. The reason being is that the steering and acceleration controls is quite a it is a very, how to say, very well tackled. It can be very well tackled without a neural network. And, there are a lot of applied mathematics even before self-driving cars that are very close. If you think about the PID controller, it is very similar to predicting the the things like the seasonal uh, temperature uh, changes and things like that. So you know it really is not necessary to as much. So this is, you can see, this is how you can do it in like how an end-to-end driving pipeline would be done. Okay. Okay. Now, right. Let's see. For now, yeah, I have read the paper, but I think I'm starting to lose steam on this here. So yeah, let's skip to the results then. So this, as you can see, so this is the result. What they did was they had several different models here. One is the imitation with dropout. Yeah, so essentially this is saying that past dropout, there are different points where the past is being removed past say speed or agent position is being removed because essentially the agent is learning from a closed loop training, and at some point most of your a lot of your information is going to be coming back from the model itself and when that happens it could go into doing weird things like if the agent haven't started slowing down for a stop sign, it won't, and then it simply won't stop, right? So this is to tackle things like that. So this the next one is the M0 with trajectory perturbation. So with some randomly nudging the vehicle away from its original position waypoint. This one is the M1 with the environment loss. Um, so environment loss would be things like the vehicle crashed into another vehicle. Um, it drove on the curb, drove off the road, things like that, right? And 3 would be 2 with less imitation. It's just lowers the weights of the expert model, and the next one will be the imitation dropout. Imitations are being dropped out. Okay. Yeah. So let's go over the results. So nudging a parked car, let's say model 0 does a very poor job. It gets stuck a lot of times, and the model 1 is like somewhat 50-50. Model 2 actually collides even more frequently, oddly enough. So model 3 with less imitation is similar to like with trajectory perturbation, but model 4 with imitation dropout crushes 10% of the time, but it's mentioned in the paper that this 10%, there are situations that most drivers would not be able to handle. Of course, there's not a perfect driver, so this is pretty, this is acceptable. Trajectory perturbation, the Model 0 couldn't do anything. It always got stuck. Adding trajectory perturbation, it became 50-50 with environment loss, 50-50, it gets stuck. So Model 3 and Model 4, so with dropout of the imitation or expert, imitating the expert, it's able to deal with this issue no problem. Slowing down for a slow car, so Model 0 it gets stuck. Model 1 has it's 5% collision. rate. Okay, so it's interesting that adding perturbation, it stopped being stuck. Model 3 with less imitation, it is able to, it's able to slow down for the vehicle correctly, and Model 4, with the imitation dropout, it gets stuck sometimes, and it tries to do some, it tries to explore some daredevil actions, and it crashed 5% of the time. Yeah, honestly, I think if I were to pick the models, I would pick Model 4 and add some safety features on top of this, and just to have it stop for a stolen car, and that would be good. Yeah, I think I will stop there because I'm just losing. I'm not feeling very well today, but yeah, I hope y'all learned about the ChaufferNet, Keras, and transfer learning, and I'll call it here. Thank you.